let's talk about the law of reflection. I am going to try and draw some really straight lines here. So hopefully I do okay. Let's see. Let's see how I do. Okay. A straight line. Okay. So this, if we were to think of like any smooth surface, so like it could be a mirror, it could be your iPhone screen or your phone screen, anything that reflects light, like a car, a really shiny car, um, anything like that. I know when I'm driving in the car with my husband and I'm playing on my phone, he says, "Can you turn that the other way? It's reflecting in my eyes." You know, anything that does that kind of thing um, is going to be um, is going to follow the same thing. So with the law of reflection, we have, so that's what this flat surface is. This is like a mirror or something like that. Then we have something called a normal, okay? And a normal is just a line that is perpendicular to that surface. If this is not a perfectly right angle, which I think I moved my hand at the last second, so I don't think it is. Let me see if I can fix it, because it's going to bother me. Okay. Now I lost phone screen. Oh well, you get what I mean. So here's my perpendicular line. Oh man. Oh well, that's as good as I'm gonna get. I'm not gonna spend all night trying to make a perpendicular line. So your normal is this perpendicular line. Okay. I'm gonna write it in red, so it's got the same color. Okay, so when they say like to the normal or anything like that, that's what they mean. They mean this line that is perpendicular. So what happens with the law of reflection? Um, with the law of reflection, we have what happens is you have light. Let me get a color, like a blue. Ooh, this one's pretty. Um, okay. Ooh, I don't know what that is. I thought I had a blue. Beautiful blue. Hmm. Okay. Well, we'll do green. Since I can't find a blue. I can't get the blue to work. That sucks. Stinks. I like blue. Okay. So your light is going to come in and it's going to hit your mirror. Okay? And we think about it towards the normal. So the normal is this perpendicular line, okay? When the light reflects off of that very smooth surface. I did not draw that well. Let me try again. Okay, that's as good as I'm going to get. When the light reflects off of that very smooth surface, okay, you're going to have, there we go. Now I get a blue. You're going to have an angle here, and you're going to have an angle here. These two angles are the same. Okay? And it's with respect to the normal. So if the first one is 30 degrees with respect to the normal, the second one is going to be 30 degrees. Okay, and they're going to call that your angle of incidence. And they're going to call this your angle of reflection. And they are going to be equal. Okay, and it's with respect to the normal. So like, I used to have a question on my test for my face-to-face students, and it would say the angle of incidence is 30 degrees with respect to the mirror. What is the angle of reflection? And there would be a choice that would say 30 degrees with respect to the normal, and a lot of kids would choose that. But remember, the first one was 30 degrees with respect to the mirror, which would be here. So that would mean that you would need 30 degrees with respect to the mirror over here, and they would pick 30 with respect to the normal, and that, that's not going to be that's not going to be the same number. Okay. So it's really important that they're exactly the same, and that if it's 30 degrees with respect to the normal, this one needs to be 30 degrees with respect to the normal. If it's 30 degrees with respect to the mirror, then you need 30 degrees with respect to the mirror. 1 second, Carol. Hey, I just had to cough, and I didn't want it on the video. I didn't want you to think that I was like dying. So do you have any questions, Caroline? Or do you want me to keep going through with this, and then you can ask questions at the end, or we can ask yours now, whatever you want to do is fine. While you're typing, I'm going to fix this. This actually undid this. Okay. Okay, that's totally fine. You know, if you have a question, just, type it in, or here, I can do your microphone. Do you have your microphone, or do you want me to just leave yours off? Fix this too. Okay. No, it's totally okay. I just didn't want to turn on your microphone for you if you didn't have it. So basically I was just this is like the second half of the electromagnetic waves, and it's basically all about light and color. So the law of reflection basically says that the angle of incidence is equal to the angle of reflection. So that's kind of what I was trying to draw here. Um, but anyway. So the next thing I wanted to discuss is diffraction. Now, diffraction is not a term that I usually use with my physics kids. We didn't really deal with it. So when I was looking it up today, I was like, oh yeah, I've seen that before. Okay, these are supposed to be in the same plane. But anyway. So basically diffraction is when you have light going in to a very small opening. Okay, this has to be an opening that's like smaller than light. And I'm going to go to an image of it in a second. And basically what happens is this light comes through here, and then as it hits that opening, it kind of like breaks up, and it creates this kind of thing, kind of like this. I'll show you the video because my picture's not great. So let me see if I can go to this link. Of course I can't. Okay, so I like going to Wikipedia for stuff like this because sometimes they have good pictures, and a lot of times they are open source. This one's not necessarily, but do you see how the light is going in, and then it's kind of making this half circle kind of pattern as it goes through that slit, that is diffraction. That's what's going on when they're talking about diffraction. And the big thing to remember with diffraction is that this slit has to be really, really small, smaller than light, like a light particle or a light wave, which is really small. So that's the little image I wanted to show you. Now let me get back to that document that I was working on. Okay, so you see I didn't do a good job drawing it. Um, that's why I wanted to have that link. Okay, so now we're going to talk about refraction. And so refraction is a little bit different. I am going to draw, I'm going to make it red like I did last time because I did a normal last time in red. And so I'm going to do it the same. So basically what happens with refraction is this is when light bends when it hits a different medium. So like when I taught in the face-to-face classroom, we had a little lab where we took a piece of acrylic, which is what this is, and we would like look at something on this side, and then we would look at something on the other side, and the kids would then draw that line, and it actually would bend. You know, they'd take their paper out and it would bend. Even though it looked straight when they were looking at it, like looking at it face on like this. Um, and so that was kind of a neat lab. Anytime, like if you've put a pencil or a spoon in water and you look at it from the side and it looks like it's bent or broken, that's refraction. So we need to work with our normal again. So I'm going to draw on this picture, and I'm going to try. Okay, that's probably about as good as I can get. And then I'm going to try. Okay. Okay. Let me do that second one again. I don't really like it. There we go. Okay. Um, so let me do a different. Okay. So if you see like this angle right here, and then this angle right here, um, this one is bigger than this one, and that's because basically when it's going into this more dense, this is air out here, and I don't know exactly what this is, but I'm pretty sure it's like acrylic. I don't know if that's how you spell acrylic, but we'll go with it. Um, so as you can see, like this angle is bigger than this one, and that's because as the light is going into this more dense medium, the light is refracting towards the normal, and so we're getting this smaller angle. Um, just like when we did reflection, this angle that's coming in is called the angle of incidence, and the angle that is, I'm just going to write that. And then this angle right here, they call that the angle of refraction. If you remember in the last one, it was the angle of reflection, but since we're talking about refraction now, they call that the angle of refraction. Doesn't like to make F's for some reason. Okay, and then we could actually do it one more. And we could do this. And you can see that if you looked at these two, this one is bigger than this one because as it's going into the air, right, which is less dense than this acrylic, it's refracting away from the normal. And so that's how you're getting that. And then actually, let me try a different color. Let's try yellow. this one, or this weird gray color, and this one should be exactly the same. And so when we would do this lab in the face-to-face classroom, the kids would actually have to calculate their percent error between this angle and this one to see, like, because they were supposed to be the same, so they could calculate their margin of error. And so that was kind of like the point of their lab or whatever. So there's lots of diagrams and stuff, but I wanted to use this real life example because you can, it's totally a real light. It's a real thing, and you can see how it's working instead of just like a fake diagram. So I thought that was kind of neat. Now the photoelectric effect. This is another thing that we don't do a lot of times in my classroom, in my face-to-face class. It is complicated. And basically, it says that the brightness increases the number of photons. And so these photons are little tiny packets of light energy. And it's basically explains this formula, remember, that we did last week. And so if you remember, your H is your Planck's constant. And then there's your energy and your frequency. So basically, as your frequency increases, your energy is going to increase as well. They have a direct relationship. And that's basically what the photoelectric effect is explaining this formula. But they mention it by name, I think, in a couple questions. So I wanted to make sure that you guys knew that it was basically talking about this formula. So when they ask you about the photoelectric effect, just kind of refer to this formula. If they say, does the energy decrease when the frequency increases, look at your formula. If you want, you can put like fake numbers in there, right? If we put and we put 5 in for F, right? Then energy is going to be 5 of what it was before, right? Because it's a direct relationship. And so you can see that if you had 5 in for energy, or you put, for frequency, or you put 10 in for frequency, that was supposed to be a parentheses, this one's going to be more energy because they have that direct relationship. So sometimes when I look at a word question and I don't entirely understand what they're asking, I'll take the formula that is similar to it and I'll just put in fake numbers. And I'll put easy numbers because it'll work the same. So then we could talk in chemistry. You probably heard this, that light acts like a wave, but it also acts like a particle. So wave will bend, light will bend and refract like waves do, but then it also does particle things, and so it acts like both, and so that's why it's so that's kind of what am I trying to say? I'm looking at my review because I want to make sure that I say what I wanted to say about that. So like when we talk about these things, we can talk about like interference, like we were talking about with our sound unit. The only the wave part of light is going to be affected by that interference. The particle part won't, right? Because particles don't act like that. Only waves do. And so I saw that question on the test and I thought it was kind of confusing. And so I wanted to just mention that really quick as well. So then we can talk about things that are luminous, which means they make their own light. And then we can talk about things that are illuminated, which means they reflect light. So for example, the sun is luminous, right? It makes its own light. A lamp is luminous because it makes its own light. But then we could talk about a reflector, right? If you have a reflector on a bike or if you have a reflector, like, that reflector tape or whatever, that it lights up, right, when it hits light, but it doesn't light up because it's making its own light. It lights up because it reflects the light that's hitting it, and that's what makes it light up. And so that would be something that's considered illuminated. Okay, if you've seen those, there are these Nike jackets that are really, really bright. And they seriously, I'm going to show you a picture, um, just because they're so neat. I mean, they are really bright. Um, I used to run in the dark, and I wanted one, and they were like $300 or something crazy. So check that out. That is a person standing in the dark with their Nike jacket. So like I said, I wanted one because I ran in the dark, but I never got one because they were so expensive. But that's literally a person standing in the dark, and that's his jacket being reflected. And so that jacket, right, is an illuminated source. It's not luminous, right? It's not creating its own light. Um, and so um, that's kind of two examples of illuminated versus luminous. So then we can talk about coherent versus incoherent light. So coherent light is when all the light is traveling in the same phase, the same direction, the same everything. Okay. And so it looks like this, right? And an example would be a laser. Laser light is so good for pointers and in all sorts of applications because that light is um, is all in the same phase. It's all going in the same place. It's only illuminating one teeny tiny part, right? When you point a laser at something, right, it's just going to do this one little part. Where like when you put a flashlight on something, it's going to illuminate this like wide area. And that's because flashlight light is incoherent, which means it's not in the same phase. It's not all in the same direction or anything like that. And so, your laser light is giving you that little pointer of light where your regular flashlight or something like that is going to illuminate a wide area, and that's because it's incoherent. Okay, so we could put flashlight here. And then I just wrote it at the bottom for you. Um, there's a question on the test. There's a huge test bank. So that's just because all of you won't get this question, but it asks basically what does laser stand for, and that's just something you're going to have to remember. And it's light amplification through the stimulated emission of radiation. And so that's basically what laser stands for. And so I wanted to go ahead and put that there for you so you would have it, um, so you can study and memorize it. And then we can talk about prisms. This is a prism, and basically what happens is white light goes into the prism, and it actually separates the light into all the different colors. And so, and you can actually see all the colors. So you can see that we've got red on the top, and then orange, and then yellow, and then green, and then blue, then indigo, and violet, right? And so we call this Roy G. Biv. When I was a kid, we learned like Roy G. Biv in art class. If you want to watch something funny that will help you remember it, YouTube, They Might Be Giants, Roy G. Biv. It is so funny. Um, and it'll help you remember. So it basically takes a white light and it breaks it into all the individual spectrums. And so that is a prism. So with a rainbow, it basically takes, with a rainbow, all of those rain droplets basically act as little prisms. And so the white light is going in and then it's separating it into the different colors. White light's going in, it's separating it into the different colors. And so basically each rain droplet is acting like a prism, which is then creating, that huge rainbow that you see in the sky. And so it doesn't actually have an end. In fact, in the videos, they say that rainbows are circular, like all the time. But it's hard to see unless you're like in an airplane or something. I've been on a helicopter trip before. Our helicopter kind of looks like this, and we could see rainbow all the way around. It was pretty cool. Not a very good helicopter drawer. But anyway, we could see a rainbow all the way around, and it was like the cockpit. All of this was glass up here, and so you could see kind of like below your feet, and so you could see the rainbow at the bottom, you could see it above you, and then you could see it on both sides. So you could see that circular rainbow. And the big thing about a rainbow is to see it, the sun must be behind you. Okay. So not behind the water, but behind you in order to get it to refract correctly, right? Because if your eye is here, right? If this is your eye and the sun is here, then you're going to see this part, right? You're going to see this light coming out. Where if you were over here, you wouldn't see that rainbow. Okay, so you have to have the sun behind you. Okay. Okay, now scattering is just when all of the light is just it's scattered. Okay, so it's when your light is going in all directions. Okay, so if you have a rough surface and light hits your rough surface, it is not going to go out like the law of, well, it will. Okay, so let's take your rough surface like this. Okay, when your light hits here, it's going to reflect out in the same angle. I didn't draw that well. Then when it hits here, it's going to reflect out at the same angle. And it hits here, it's going to reflect out at the same angle. And it hits here, it's going to reflect out at the same angle. So even though each individual, bit of light is following the law of reflection, because the surface is not smooth, it's rough, the light is going all over the place. Okay, and so when you're trying to decide if a surface is smooth or rough, you can kind of think about like in real life. Like we had an example on a test when I was teaching they would say paper, and kids would go, "Oh, paper's pretty smooth." Yeah, but if you shine a light on paper, is it gonna reflect back like it would on your iPhone screen? No. And so paper's technically considered a rough surface because the surface is kind of like